Hello and welcome to the Maths Experience tutorial video in association with DCU University Dublin. In this video we'll have a look at modulus inequalities, differentiation and implicit differentiation. Right, so the first question we'll look at is a modulus inequalities question. You're given the equation the modulus of 3 over t minus 4 is less than or equal to 2, and we have to solve for t. So the important thing to remember with modulus inequalities question is that because we're dealing with a modulus, we have to consider both the positive and the negative real values that will satisfy the equation. So what we're going to do here is we're going to deal with the positive value first and the negative value secondly. So to have a look at the positive value, we'll take 3 over t minus 4 and we'll multiply it by plus 1, which just leaves it exactly the same. To look at the negative value then, multiply that by minus 1 and we'll get minus 3 over t plus 4. So we'll take the positive value first. What we're going to try and do is get t on its own. We're going to try and isolate t. We have 3 over t minus 4 is less than or equal to 2. We need to get all the integers to one side and everything with the variable t on the other side. So we take minus 4 across and it changes to plus 4, and we end up with 3 over t is less than or equal to 6. Remember that when minus 4 comes across, it becomes plus 4. Right, so now we have 3 over t is less than or equal to 6. Now there's a bit of a booby trap here. Most people would be tempted to multiply across by t, but t could be a minus number, could be negative. And if we did this, if we multiplied across by t, it would change the inequality sign. Since we don't know whether it's plus or minus, what we do is we multiply it by t squared, which is definitely positive. Any number squared has to be positive, it can't be negative. So when we multiply across by t squared, we end up with 3t is less than or equal to 6t squared. We bring the 6t squared across, then we factorize out, and we end up with t multiplied by 3 minus 6t is less than or equal to 0. We then take both these factors and we put them less than or equal to 0. So first of all, t is less than or equal to 0, and then we take 3 minus 6t is less than or equal to 0. The 6t goes back across and we end up with t is greater than or equal to a half. So we're left with two answers. What we now need to do is we need to sub these answers back in to our equation and see if they work. So first of all, the t being less than or equal to 0, if we put that back into the equation 3 over t is less than or equal to 6, we get 3 over 0 is less than or equal to 6, which is undefined. You can't have 3 over 0, so that's false, it's not a solution. If we put t being equal to a half back into our equation, we get 3 over a half is less than or equal to 6. 3 over a half is 6, so that is less than or equal to 6. So that's true, t is greater than or equal to a half. Now we follow the exact same procedure for the negative value. So again, we bring all the integers to the right hand side and we leave anything with the variable t on the left hand side. So when we do this, we end up with minus 3 over t is less than or equal to minus 2. Now we never like having minuses on both sides of the equation, so what we'll do here is multiply both sides by minus 1. But remember, when you multiply by minus 1, you need to change the direction of the inequality sign. So minus 3 over 2 is less than or equal to minus 2 changes to 3 over t is greater than or equal to 2. So here again, we're left with a potential booby trap. You can't multiply across by t because t could be negative, could be positive, we don't know. So again, we multiply both sides by t squared, which is definitely a positive number. When we do this, we end up with 3t minus 2t squared is greater than or equal to 0. We factorize out again, and we get t is greater than or equal to 0, or else 3 minus 2t is greater than or equal to 0, which gives us t is less than or equal to 3 over 2, which is 1.5. Once again, we test our answers. The two answers being t is greater than or equal to 0 and t is less than or equal to 3 over 2. We put them back into our equation, which is 3 over t is greater than or equal to 2. When we put 0 in, we get 3 over 0 is greater than or equal to 2, which again is undefined. 3 over 0, we can't have that. So that's false, that's not a solution. When we put 3 over 2 in, we get 3 over 2 is greater than or equal to 2. And that gives us 2 is greater than or equal to 2, which is true because 2 is equal to 2. So that means that t is indeed less than or equal to 3 over 2. So then we take both our answers and we combine them together. So the first answer we got was that t was greater than or equal to half. The second answer we got was that t was less than or equal to 3 over 2. So when we combine them, we get t is greater than or equal to half, less than or equal to 3 over 2, which basically means that if the value of t is anything between half and 1.5 inclusive, the equation will work. If t is anything outside of those values, the equation won't work. And that's the end of the modulus inequalities question. So now we shall move on to the differentiation question. So this question looks quite scary, but it's actually not too bad if you follow the simple steps. We're told that p of t equals minus 1.7t cubed plus 72t squared plus 7,200t plus 80,000. That's the population of a city t years after 1950. And we're asked what was the population growth rate of the city in 1990. So you have to ask yourself, what are we being asked here? We're being asked for the growth rate of the city, which refers to rates of change. Growth rate is rates of change. And rates of change means differentiation. And just a reminder of the basic differentiation rule. If you were to differentiate 3t to the power of 3, the 3 would come down to multiply by the 3, and the power 3 would be reduced by 1. So 3t to the power of 3 goes to 3 multiplied by 3 by t to the power of 2, which gives you 9t squared. And when we differentiate a constant, that's any number without a variable in it, such as 500 minus 2, a half. When we differentiate any of those numbers, we're left with 0. Right, so again, this equation looks quite scary, but if you're just neat and follow the simple steps, it's not too bad. So we're told that p of t equals minus 1.7t cubed plus 72t squared plus 7200t plus 80,000. We bring the 3 down to multiply it by the minus 1.7, and we get minus 3 multiplied by 1.7t squared. Then in 72t squared we'll bring the 2 down and multiply it by the 72 to get 2 by 72t. Remember, the t squared has been reduced to t to the power of 1. The 7,200t is essentially 7,200t to the power of 1. So the 1 comes down and multiplies by the 7,200. The t is reduced to t to the power of 0, which is 1. So that just leaves us with 7,200. Then finally, the 80,000 is a constant. So remember, no matter what the constant is, no matter how big or how small, we're always left with 0. So that gives us our new equation, which is p dash t equals minus 5.1t squared plus 144t plus 7,200. And notice how the powers have decreased after we have differentiated. Okay, well, the second thing we need to figure out is what value we use for t. We are told that t is the number of years after 1950. Since we're being asked to work out the growth rate in 1990, that's 40 years after 1950, so t is equal to 40. So then what we do next is very simple. We take our 40 for t and we sub it in to our equation everywhere we see t. So we get p of 40 equals minus 5.1 40 squared plus 144 by 40 plus 7,200, and this will give us the population growth for the city for 1990. And when we work that out on our calculator, we get that the P of 40 equals 4,800, which means that the city grew by 4,800 people in 1990. And that's the end of the question. Okay, so our final question is an implicit differentiation question. Again, this looks very difficult, but if you are neat in your work and follow the simple steps, it's actually pretty easy. So the question says, use implicit differentiation to find dy dx where 4xy cubed plus x by cos of y equals 2x. So the simple steps that I spoke of regarding implicit differentiation are as follows. Firstly, we differentiate both sides of the equation with respect to x, treating y as a differentiable function of x. Then we collect the terms with dy dx on one side of the equation, and then we solve out for dy dx. In this question we have two products on the left hand side, so we'll use the product rule to solve them. So because this is a little bit convoluted and could get a little messy, we'll look at them separately. So first of all, we're going to take a look at 4xy cubed and solve that using the product rule. Now remember, the product rule can be found in your maths log tables. So using the product rule, we will put u equal to 4x and we'll put v equal to y cubed. Then to differentiate u equals 4x, u becomes du dx, and 4x, which is 4x to the power of 1, just becomes 4 because the 1 comes down to multiply by the 4 and the power of 1 is reduced to 0, so x to the power of 0 is 1. So we end up with du dx equals 4. For v equals y cubed, you'll notice we have no x in that, but we're differentiating with respect to x. So the v becomes dv dx, the y cubed becomes 3y squared because the 3 is brought down in front of the y and the power of 3 is reduced by 1 to 2. But you have to multiply that by dy dx because remember, we're differentiating with respect to x. So that's 4xy cubed sorted. So now we focus on x multiplied by cos of y. Again, we use the product rule. X is substituted in for u and cos of y is v. So if we differentiate u, we get du dx, and when we differentiate x, which is x to the power of 1, remember, the 1 will come down, which becomes 1, and x is x to the power of 1, which reduces to x to the power of 0, which is 1. So we're just left with 1 multiplied by 1, which is 1. Then to concentrate on v equals cos of y, the v becomes dv dx because we're differentiating with respect to x, and the cos of y becomes minus sin y dy dx. You'll find that in your maths tables that cos differentiates to minus sin. So then we're using the product rule, which I said you can find in your maths log tables. And the product rule states that dy dx equals u by dv dx plus v by du dx, and we'll sub in our two equations. So as we said, if u is equal to x, du dx equals 1. If for v we have cos of y, our dv dx is equal minus sin y dy dx. And subbing these into our product rule, we get dy dx equals x multiplied by minus sin y dy dx plus cos of y multiplied by 1. And when we multiply out these brackets, we get dy dx equals minus x by sin of y dy dx plus cos of y. So we originally had 4xy cubed plus x multiplied by cos of y equals 2x. What we now have is 12xy squared dy dx plus 4y cubed plus minus x multiplied by sin y by dy dx plus cos of y is equal to 2. Remember, the 2x was differentiated to 2 because x is to the power of 1. That comes down to multiply by the 2 and reduces the power on the x to 0, which just makes the x become 1. We're now on track to find dy dx. So the next step is to take everything with dy dx and move it to the left hand side and put everything else on the right hand side. So our new equation is 12xy squared dy dx minus x by sin y by dy dx equals 2 minus 4y cubed minus cos of y. We then take out dy dx as a common factor, and we get dy dx multiplied by 12xy squared minus x by sin y equals 2 minus 4y cubed minus cos of y. And then we just divide both sides by 12xy squared minus x by sine y, and finally we get dy dx equals 2 minus 4y cubed minus cos of y over 12xy squared minus x by sine of y. And that's our answer. Thank you for watching.